Our problem statement is there are some difficulties with the methanol water separation process, which are possibility of energy waste and restriction on reaching the required purity levels. And there are some raises operating expenses and decreases throughput due to drops or other undesirable behavior. For our aim, the aim is to assess the methanol water separation procedure utilizing a distillation column. Besides that, it is to investigate thermodynamic concept, evaluate operation difficulty, and suggest enhancement for improved process sustainability and performance. Our objectives are to analyze the methanol water separation process using a distillation column. Besides that, the objective is to evaluate the efficiency and effectiveness of the separation in achieving target purity levels. There are some key processes parameters that being focused, which are feed composition, reflux ratio, operating pressure, energy input to boiler, number of stages, heat integration, thermodynamic models, and column temperature profile.
Hi, my name is Eliza Joffrey Binti Morris and my metric number is 98023. And I'm going to present on the simulation with Aspen part. So the first step is to choose the template, which is specialty chemical with metric unit. Then after that, we rename the file as methanol water separation. After that, we fill in the components, which are methanol and also water. And then we set the method filter to be common, and then the best method DSA and RTL. After we finish with the property part, we proceed to the simulation. So this is the diagram that we got after we finish our drawing. So we choose the column and then we choose the distillation and then we name it as distillation. And we have three streams. The first stream is the mixed stream, which consists of methanol and also water. And then the top stream, we name it as distillation top. And then the bottom stream, we name it as distillation bottom. Next, after we are done with the diagram, we fill in all the required data. So the first one is for the distillation. So the number of stages is 10, the feed stage is 5, the reflux ratio is 2, and the distillate to feed mole ratio is 0.5, and the condenser type that we choose is total. So for the pressure, for both condenser and boiler pressure, we set it as 1 atm. And then next for the mixed stream, we set the temperature as 25 degrees Celsius, and then the pressure is 1 atm. And for the total flow basis, we do it in mole, which is 100 kilomole per hour. And for the mass fraction, for methanol and water, both are set as 50 and 50, so the total is still 100. Lastly, this is the result that we got after we run the spun file. As you can see at the bottom stream, it is rich in water, and for the top stream, it is rich in methanol.
My name is Verla Busa Matias and my metric number is 98983. I will discuss the optimization of key parameters. Firstly, the reflux ratio directly impacts the separation efficiency and energy consumption of the distillation column. Initially set at 0.5, the reflux ratio was increased incrementally to evaluate its effect on product purity and energy demand. Higher reflux ratios led to improved separation, resulting in higher methanol purity in the distillate and reduced water contamination. However, the energy input to the reboiler and condenser also increased significantly with higher reflux ratios. An optimal reflux ratio of 0.8 was identified, offering a balance between product purity and energy efficiency. The feed stage location determines the interaction between the ascending vapor and descending liquid streams in the column. The feed was initially introduced at stage 5, which resulted in moderate separation efficiency. To optimize the process, The feed stage location was varied between stage 4 and 6. The results show that introducing the feed at stage 4 slightly improved separation performance by providing better alignment with the methanol-rich vapor phase. This adjustment enhanced the methanol recovery in the distillate while maintaining energy requirements within acceptable limits.
So now I will talk about our proposed improvements. First is by using advanced distillation configurations. It can be difficult to separate methanol and water, particularly if they have similar boiling temperatures or form azeotrophs. Using sophisticated techniques like extraction distillation or pressure swing distillation (PSD) is a good substitute. Extraction distillation employs a third ingredient such as glycerol to assist separate the components, while PSD uses pressure changes to facilitate separation. This involves modifying the reflux ratio, feed position, and tray count. This results in a separation procedure that works better and consumes less energy, particularly when azeotrophs or close boiling point cause problems for classical distillation. Next is improving energy efficiency. Since distillation involves heating the mixture, it frequently consumes a lot of energy. The method of reusing energy is an excellent substitute. For instance, the feed steam can be preheated using the heat from the distillation condenser. As a result, less heating is required. Options for heat integration may be investigated with a spent energy analyzer, and the process can be optimized by modifying variables such as feed temperature and pressure. This strategy has the advantages of less environmental effect, cheaper expenses, and less energy use. It's a more intelligent and environmentally friendly method of distillation. Last but not least is choosing the right thermodynamic model. Accurate modeling is a key to designing a good distillation process. Methanol and water don't behave ideally, so picking the right thermodynamic model is important. Models like NRTL, Uniquac, or Wilson can be tested in Aspen to see which one best predicts the behavior of the mixture. To improve accuracy, the chosen model should be validated using experimental data or data from literature. By testing different models and checking the results, the best one can be chosen from the simulation. Choosing the right thermodynamic model ensures that the distillation column works efficiently and effectively. So this is our conclusion by answering M and our objective. In summary, the Aspen study of the methanol water separation process shows how well distillation works to produce high purity methanol while emphasizing how crucial it is to maximize energy use. The research effectively assessed the process thermodynamic underpinnings, pinpointed operational issues, including refractory ratio and column efficiency, and suggested improvements to boost performance and sustainability. These results highlight how process optimization may lower inefficiencies and aid in the creation of a separation system that is more sustainable and energy efficient.